First statement is CLC, clear command, clear all. So it clears all variables, close all, it clears all windows if opened. So T is equal to input, enter the duration of the samples. So input is the function, just like a scanf function, to take the input value from the keyboard. So that is assigned to the T. So fs is equal to input, enter the total number of samples. So it takes the total number of samples from the keyboard, assigned to the fs variable. And when we are calling vm is equal to input, it takes the amplitude of the message signal from the keyboard, assigned to the vm. It takes the input value that is amplitude of the carrier, assigned to the vc variable. So input, enter message signal frequency, it takes the message signal frequency from the keyboard, assigned to the fmsg variable. So it calls the input function, it takes the carrier frequency, assigned to the fs variable. So it takes what is another line, m is equal to input, enter the modulation index. So it takes the modulation index from the keyboard, assigned to the m variable. Assigned to the m variable. What is this? T is equal to point, T is equal to 0 colon T by fs colon T. So it is the time column matrix T. So it creates column matrix T. Okay. So ms is equal to vm sin of 2 pi message signal fmsg into T. So each value of T is substituted, so it creates another column matrix msg, already discussed in the first program. Okay, so it creates message samples. So we are going displaying message signal 4, 1, 1, first plot. So plot of T comma f, T comma msg. So plot of x by x label and y label and title. So title is the message signal. So coming to the carrier signal is equal to vc star sin of 2 pi fct. So 2 pi fct. So T contains matrix, column matrix. So each element of this column matrix is substituted. So it produces number of samples for each. It produces each value for each element of the T column matrix. So finally carrier samples are generated. So subplot 4, 1, 2, it is a second figure. Third argument indicates second figure. So plot of x comma y, x label, y label, title. And see here fmd is equal to vc star sin of 2 pi fct plus modulation index into cos of 2 pi fmt. So this is the expression of the fmd. Now fm signals are stored in the fmd. So here message samples and the carrier samples are substituted and it produces fm samples. So fm samples are now displayed. So plotting the fm signal. So that is third figure. So plot of T comma fmb. So it displays third figure, FM signal. Now FM signal is created, that is present in the FMD column matrix. Now we are calling diff of FMD. So diff function takes the difference of two previous samples. It produces a difference of two previous samples, stores in FMD1. So we are checking the FMD1. Any element is less than 0 and putting 0. So next we go through the Butterworth filter. So it requires positive values. So that's why any negative value present in the FMD1 signal, so we are making 0. Any sample is less than 0, so we are assigning 0 to the FMD1. So use a Butterworth filter. So we are calling Butterworth filter for demodulation of FM signal. So what is that? See here. So we are calling butter function. So butter function, when we are calling, so it takes two arguments. So first argument is 2 and second argument is 2 comma 5 comma FM SE. Message signal by 2000. Okay. So here the first argument tells the order of the Butterworth filter, second order Butterworth filter order, and second argument is normalized frequency, normalized angular frequency. So 2 pi FM by 2000 indicates it is a normalized frequency of the Butterworth filter. Okay, now we are calling butter. So in this way, butter function in this way, so it returns two column matrices. One is den, other one is num. Okay, Butterworth filter contains requires numerator coefficients and denominator coefficients. Okay, Butterworth filter requires numerator coefficients and denominator coefficients. So now we are calling Butterworth filter function filter. So now we have to pass the denominator coefficients and numerator coefficients to this function as arguments. Okay, so and what is the input for this one? FMD1. So FMD1 is the input signal. Okay, so it produces filter output 1. Again we are calling filter, that means we are using again second stage of filter. Again you have to call the filter function, again you have to pass the denominator coefficients and numerator coefficients as arguments. So we have passed the den and num matrices as an argument to the filter function and filter output 1. So what is the third argument? Filter output 1. So filter output 1 is the output of the first filter. Now second filter produces filter output 2. So filter output 2 is the output of the second filter. So it is the final demodulated signal. After passing two Butterworth filters, so demodulated signal is obtained. So filter output 2 contains demodulated samples. So fourth figure, that is a demodulated sample. So we are calling subplot 4,1,4, fourth figure. Third argument indicates plot number. That plot number is 4. So plot of x comma y, and x-axis is t and y-axis is filter output 2 samples. So filter output 2 samples means it contains demodulated samples. So calling x label and y label and title. So this is the end of the second program. So you have to enter all the values. So time duration. So time duration is 1. Okay, total number of samples is 1000. Amplitude of the message signal is 5. amplitude of carrier signal is 5. So message signal frequency is 8, carrier frequency is 100. So modulation index is 10. So you will get the plots. So message signal, and this is the carrier signal, this is the FM signal. So if you observe FM signal, so sometimes more number of cycles, that means maximum frequency, sometimes less number of cycles, that is less frequency. So the frequency of the carrier signal is varied according to the modulating signal. So during this period, so modulating signal voltage is high, that's why the frequency is maximum. So during this period, so modulating voltage is less, so there are less number of cycles. So that's why you will see the variations of number of cycles in the FM signal. So number of cycles is nothing but frequency. The frequency is varied according to the modulating signal. Now this is the waveform of the demodulated signal. It is the same as the modulating signal, message signal. So that is all about